So this is what we have covered so far. You can go through the recordings, anybody who missed it. Protocols, topology, differences between hubs, bridges, switches, and collision domains and broadcast domains and cables, and role and function of network components like routers and layer 2 and layer 3 switches, next generation firewalls and IPS and access points. Controllers will be talking in depth again, detail later on. Don't worry. Endpoints, servers, power over Ethernet, TCP/IP, this protocol suite, and OSI reference model, and source and destination port numbers, and of course this TCP and UDP, all these things, right? Three-way handshake, sliding window concept. Now, this is again theory. After this, we should be here quickly, and we'll be getting into now IP addressing and subnetting. So, anybody who doesn't understand this IP addressing and subnetting, all your doubts will be cleared there. We'll be spending around 3, 4, I don't know, 3, 4 lectures on that. Yeah, maybe minimum 2, 3, maybe 4. Okay. Cables we have done. We have looked at a bit of uh, cables, copper cables, namely rollover, crossover, and straight through, like Cat 5, Cat 6, right, and all those things. Cat 6A, Cat 7, single mode and multi mode fiber, and point to point and shared media, Ethernet shared media. Point to point connections, right? Point to point and Ethernet shared media. So point to point is just between two routers, or right, whatever. Now, if you take a connection between this headquarters and this branch, this could be in India, that could be in maybe Australia, right? Of course, to the WAN. So it will be connected to the ISP's routers and like this, multiple routers, right? In between. So this can be a point-to-point connection, right? Maybe a MPLS point-to-point connection. In the olden days, it was serial point-to-point. Then we used to configure lease lines and frame layer virtual circuits. That's gone. But today it can be MPLS, right? Point-to-point MPLS VPN connection, right? Point-to-point. And this network is known as a broadcast type of a network. You may have multiple routers here. You may not have multiple routers, but this is a broadcast type of a network, also known as multi-access type of a network, right? Also known as our LAN. Yeah. Because if one device gives a broadcast, it will go to everybody else. That means broadcast is permitted here, right? There are different names to same things. So therefore, he's talking about multi-access and point-to-point connections. Ethernet shared media. That LAN is also known as Ethernet shared media, right? Specifically, when we were using hubs, that was half duplex. But nowadays we have switches, so full duplex. Okay. Yet you can call that Ethernet shared media. So connections we know can be point to point or can be in a broadcast type of a network like Ethernet shared media. Okay. Compare physical interface and cabling types. So physical interface, uh, I told you in the this is now gigabit, right? Maybe 000. This is gigabit 001 port. I mean just two ports. But in the olden days, I told you it was like this symbolically, right? And these were supposed to be serial ports, right? Could be serial 0 or serial 0/0 or serial 0/0/0. Like the connections were like this, serial ports. And there used to be a box here, CSU, DSU, whatever. Anyway, this is all gone now. This was olden one, right? So we used to configure serial point-to-point connections between head office and branch office. That is also known as leased lines, right? Leased line. So ISP has got a lot of bandwidth, and I'm going to lease some bandwidth from the ISP. So it will be totally private, right? That means communication between just two of us, right? No interference. That was serial. Alternatively, if we don't configure this, we if we didn't configure that in the past, right? Years ago, we could have configured here because the encapsulation here was HDLC, or you could have changed it to the better one, PPP, point-to-point protocol for this lease lines. But in case we want to use some other technology here, I mean, I'm talking about the one which is nobody's using today. We could have taken a serial port which had 60 pins, 60 pins, right? 60 pins like this here, the interface, and the encapsulation was by default HDLC, high level data link control, and we could have changed it to PPP, but all these things are gone now. And it was slow. Why? Because the speed was only 1544 kbps, which was equivalent to 1.544, which means Mbps. What are we talking about, man? 1 MB. We are talking about here 1000 Mbps. Gigabit means what? 1000 Mbps, right? So 1000 times faster. So this was slow. So gone. Legacy now, right? So types of interfaces, see, serial ports were different. They had 60 pins, and the encapsulation was HDLC, and we could have changed it to PPP or maybe frame relay, right? So we could have configured frame relay also. That was another technology, right, which we used to use in the olden days to configure, to communicate through frame relay virtual. So this logically, frame relay virtual circuits were created, right? And these were all frame relay switches inside the cloud, ISPs. So all gone now, old technology, right? Frame relay. So that was known as non-broadcast multi-access technology because over this circuit, right, broadcasts were not allowed. And what actually broadcast, what is it that was not allowed, but what actually is a broadcast between these two routers? So if you configure in the olden days, if you configured India and Australia head office and branch office intra network, right? Isn't it? Uh, if we had in the olden days configured RIP1 routing protocol version 1 or IGRP, which is dead today, on this, you configure either of the two, right? Either RIP1 on both of them or IGRP on both of them. So every 30 seconds, supposing if we configure RIP version 1 routing protocol on these two routers, both these routers, they will exchange routing table updates every 30 seconds, but they will broadcast, right? Automatically, the IP address of that routing update will be 255.255.255.255, right? And the MAC address will be FFFF. This is the MAC broadcast, right? FFFF. So they were not allowed when you use frame relay, right? Therefore, the technology was known as non-broadcast multi-access. Now, this is only an example of point to point, but frame relay could have been like this also. This is electric symbol, right? R1, serial port. We could have had multiple branches, Japan, Singapore, Australia, Mumbai, Delhi, Chennai, Calcutta, whatever, right? And this is our headquarters. So from here, we could have multiple virtual circuits, frame relay virtual circuits, right? All this old legacy technology. But this technology could have been known as point to multi-point also, right? Okay, but you don't have to bother about frame relay and lease lines and HDLC and PPP and serial ports. Nothing in your course, all old things. But because they said, tell them what are the types of interfaces. So I'm telling you, right? Compare the physical interface, right? And cabling types. So if we go on Google, let's say, uh, serial ports on Cisco router. ये क्या है यार? Okay. So serial ports had 60 pins. See this. The serial port कहाँ है? Hmm. Yeah, look at this. Is it serial port? Can I see anything here? No. No, this is not that serial port, man. What I'm looking for is, look at this. This is serial. See that? It had got 60 pins. And that the cable used to connect to the ISP's router, right? They're also serial port, both the sides. But that's old, legacy one. क्या हो रहा है? What's happening? See this? Serial, there are two serial ports, right? One lease line can go to maybe London, and maybe from here you can have a point-to-point or a multi-point, point-to-multi-point frame layer virtual circuits going to another ISP, right? Or another port of the ISP. So like these are multiple serial ports. This is all gone now, 60 pins, right? So this is gone, but nowadays we don't use the serial ports, we use only Ethernet ports. Okay. So types of interfaces. These are the two types of interfaces. Of course, we had BRI interfaces also. That was used for ISDN. That was just like RJ45, right? Used to go to telephone company from our router. Understanding? Yeah, everybody. So in the olden days, we had BRI ports, basic rate interface. So they were just like this RJ45 on our router, right? So this used to go to the telephone company, right? Whatever their device is there. This is one. So BRI ports. I told you about serial port. Serial port, the symbol is electric symbol, right? And these are serial port. 60 pins. I just showed you the how the port looks like right here, like this, 60 pins. And this will be connected to the ISP's router. Again, a serial port there. But nowadays, we are just connecting Ethernet to Ethernet, right? ISP, Ethernet, that means gigabit Ethernet, right? Whatever. You know, basically, Ethernet is 10 Mbps, olden days. Fast Ethernet is 100 Mbps. Everybody knows this, right? But nowadays, we are using gigabit, so 1000 Mbps. Or could be 10 gig, or could be 40 gig, right? Or could be 100 gig, whatever. So, but essentially, it's Ethernet, right? So, Ethernet over WAN nowadays. Earlier, Ethernet was only in the LAN because serial, that WAN connection, right? Serial port, it was there, olden days. But now we have Ethernet in the LAN as well as WAN. So, where are we? So, can I remove all these things, guys? We have discussed a bit of all these things, except for this one, last one, which I'll tell you quickly. Can I remove this? I guess समझ में getting some rough idea. Rollover, crossover, straight through that cable types we have discussed, right? And in fiber optic, we have single mode and multi-mode cables, depending on the distance and cost, right? Whether ISP is used or we use it for the home. So cables can be copper or fiber optic, or nowadays we can also go in for wireless. So cableless wireless. Can I remove strike of this? All these things. Yes, guys. Three things that I have selected. Everybody. Yes or no? Yeah. Well, nothing is clear. Yes or no? Everybody. Yeah. Yes. Voice is breaking a lot, but I think I can remove them. Is it okay, guys? Everybody need to answer, man. So, yeah. Yes, it is. Yeah, I've removed these three, and I'll tell you more about this in the practical. Okay. So, what is this now? Describe characteristics of network topology architectures, right? We're looking at topology architectures. So now we have seen TCP/IP model, we have seen OSI reference model, right? And Now we look at this little bit tidbit theory, right? Two tier, three tier. Right, let's have a look at this. So what is this two tier, three tier, one tier? They have not mentioned. Nobody's mentioning one tier. I only mentioned one tier on my own, right? But yes, two tier, three tier. So we have a small size of a network branch, right? Or the branch could be medium branch, right? Size of the network, or it could be a big branch, right? Branch. Okay. So now if we look at the big branch, I am telling you how designing is done, right, in the real networks companies. So in a campus, we may have multiple buildings, right? N number of floors, correct? We may have multiple buildings in a campus, and every floor will have users and switches, right? So I'm taking old scenario. These lines mean they are switches, right? I'm just drawing them as lines. Right? Every floor will have maybe multiple switches, and end users will be connected here like this, right? So something like this. Okay. So this is a big branch with at least four buildings, right? So now these are, let's say, layer two switches. Ah, so they may have 12 port, 24 port, 48 port, whatever number of ports. Right? These are access layer switches. Access layer switches. Right? Let's say they are layer two switches, older one. So you may connect here servers or end users or whatever, right? Or access points or wireless LAN controller, whatever, or IP phones, right? Or video cameras, whatever. And then we had multi-layer switches. So we call them distribution layer switches. This is just symbolic, right? Actually, I could have drawn the same diagram above also, right? Like this, depicting some ports here, right? So imagine they're all same, right? But just that these ones down below are layer two, and these are layer three switches, right? So they are known as distribution layer switches. So they can do routing as well as switching. And look, every access layer switch is connected to every distribution layer switch. So if I keep on drawing this, you get the thing. Every access layer switch is connected to every distribution layer switch. I'm not drawing all of them because it will take a long time, man, also. Right? But you get the funda, right? And then we have core layer switches. They are also multi-layer switches, but high-end, very costly. Again, every layer switch will be connected to every core layer switch. Let's say like this, right? And finally, sky blue color. ISP1, ISP2, right? Different ISPs. Everybody connected to both ISPs. Got it? This is how in one building communication can happen like this. This is how you design your real life networks. In amongst them, so these are core layer switches, right? Both of them above. So they are again multi-layer switches, layer three switches, right? Layer three switches. They are layer three switches. Or you can call them multi-layer switches. But let's say down below, I'm taking an old scenario. These are all layer two switches. But look, observe, none of the layer two switches connected with each other, right? But if this guy needs to communicate with this guy here, it is just going to be of just one hop. See, it can go like this and communicate like this, or it can go like this and communicate like this. So if this link fails, it can take some other path. Got it? So this is how you create redundancy, isn't it? That means if one device fails or one cable fails, you can communicate through another cable or another device, right? So this, okay. So now, you will be configuring port security here, right? VLANs and port security and all those things, right? Here, here between the access layer and distribution layer, we can configure ether channels, right? Layer 2 ether channels, which we'll talk of later on, don't worry, right? We'll be talking of all these things later on. So between any access layer and distribution layer switches, we can have multiple cables and we can bundle them together. So logically, the throughput will increase bandwidth, and that's known as layer 2 ether channels. But don't worry, we'll talk of this. I'll explain this in more detail, practical theory, everything later on. In between the distribution layer switches and core layer switches, we can have layer 3 ether channels, right? Layer 3 ether channels. Don't worry. We'll talk of all these things later on, right? So we are bundling them to increase the bandwidth, right? Something like this. Okay. Now, what's the function of a core layer switch? Maybe you have a data center in the cloud, and this guy immediately wants to download something from that server, right? So his job is to core layer switches, right? To quickly get the data and provide it to the user here, right? So all fiber optic cables and fast connectivity and theoretical core layer switches, they should be able to adapt to changes quickly, right? Something like this. So you just have to read this in the theory, but all theoretical. What about distribution layer switches? These ones. Look, all the cables from the access layer, they distribute at the core layer. All the cables coming from above core layer, they also, sorry, all the cables coming from access layer and core layer, both the lowest layer and the highest layer, right? They all aggregate where? At the distribution layer, isn't it? Correct? And the distribution layer switch can act as a default gateway for this access layer switches. Okay, default gateway. So this is your three-tier hierarchical model, wherein you have a core layer, you have a distribution layer, and you have access layers. Between the distribution layer and core layer, you will be configuring routing. That means OSPF or RIP or EIGRP, right? Something like that. So VLANs and all those funda will not extend to distribution and core layer. They'll only be limited to the access layers. So when you have a big network, this is how you got to configure it. So in other words, I'm still not done with it. So in one building, we'll have access layer switches. Now I'm cutting short the diagram, and then they will be connected to distribution layer switches and distribution layer, right? Like this. In every building, you'll have every floor, you'll have access layer switches, right? And of course, they'll be having end users on every floor connected to the switches. And the access layer switch every will be connected to every distribution layer switch in the same building. Every access layer switch will be connected to every distribution layer switch in the same building. You get it? Like this. Okay. Now this is one building. So all other buildings, similar scenarios. Got it? So I'll remove this guy. So we have what? Access layer switches and we have what? Access layer switches and distribution layer switches, right? Multi-layer switch. So every access layer is connected to every distribution layer switch, right? Every building. Similar? Yeah. So imagine the same diagram here, same diagram here. But in one building only, we'll have access layer switches similar to other buildings and this distribution layer switches again like this. And in this building only we'll have core layer switches also, right? So only one building has got, let's say, core layer switches. These are your core layer switches, right? Now, every distribution layer switch will connect to both core layer switches. From every building, every distribution layer switch will connect to every core layer switch. From every building, every distribution layer switch will connect to every core layer switch like this. Got it? And finally, I don't have space there, but finally, this will connect to one ISP. So we have two ISPs and this one also here. And this one will also go to the ISP. Got it? So this is how you design your networks when your network is big enough. That means you have at least or more than four buildings in your campus. Okay. So what is the three-layer model? We have access layer switches, we have distribution layer switches, we have core layer switches. These are all layer 3 switches. This is in the olden days it was layer 2. Nowadays you may find all of them layer 3 also. But this is for a applicable for a big size of a network. What if you have medium size of a network size? So we'll have access layer switches, right? Whatever. And we'll have like this connections. Okay. This is this is access layer switch. This is distribution come core, right? So this is a layer 3 switch. Let's say presumably these are layer 2 switches. Okay. This is all layer 3 switch. And now this, will go towards the ISP. ISP1, ISP2 in the cloud. I'm not changing the color now. Get it? ISP1, ISP2. So this is distribution come core. We also call it, it's also known as collapsed core, right? Design. So this is two-tier hierarchy, right? This is your two-tier hierarchy. We saw for big three-tier, right? Wherein we had access layer and distribution layer and core layer. Now two-tier. And if you have a very small branch, just 3, 4 employees, remote branch, not very important, you may just keep one layer route layer 3 switch that will connect to ISP. I'm taking a very remote example. If this cable fails for 2 days, there's no connection, then also presumably this is a very small branch. Not much is going to change or happen. Very remote example, right? But something like this. Okay. Or for that matter, you may also have connection to two ISPs. But this is access layer come core layer come distribution layer, right? You have end users connected here. This is only router come switch, right? So it's a multi-layer switch. That's it, just one switch. Okay. That too, it may be just one ISP or it may be two ISPs. Okay. So this is your single tier, which is not mentioned. But Cisco has asked us to talk about two tier and three tier. So we have discussed this. This is for large size of networks. This is for medium size of network, right? So this is for more than four buildings, at least four buildings, right? So if you have just two or three buildings, maybe you can go in for two-tier hierarchy. So everything depends on cost, right? More the devices, the more the money you have to spend. Okay, guys, are we done with OSI? Are we done with TCP/IP? Are we done with TCP model, TCP/IP? Now we are done with what? Yeah, we are done with here. Can I strike off two-tier and three-tier? Yes, guys. Now, can I strike it off? Understood? Model, how you design your network, how you connect your devices, the real life companies. Yes, guys, anybody here? Can you hear me? Yes or no? All theory. Aditya, Dipti, Megha, and Neeraj.
Yes, teacher.
Now, yes? Understood the concept, right?
Yeah.
Okay.
Yeah.
Now, spine and leaf is actually used in data centers only, right? Data center. I'll show you a slide later on for spine and leaf and spine and leaf. So, in the data centers or maybe your enterprise, we have racks like this. In the racks, what do you have? We have servers connected like this. In the olden days, they were like this, right? They were kept on the desktop, right? They're standing. But nowadays, they are flat and they are nut bolt connected like on the rack. So these are your servers, maybe in the data center, in your rack. And here you have a switch here, right? Again, top of rack switch, you call it. So again, one server will be connected to multiple switches, right? Something like this. I'll show you the diagram later on, right? Every server will be connected to. So maybe I'll extend this rack and we have two type of rack switches. So every server will be connected to both the switches, right? And then you have, I think, one more switch here. So, okay, let's not get there. I'm not getting the exact diagram. So these are servers and these are switches, right? So this is also known as top of rack switch, right? So this kind of a topology is known as spine and leaf, right? But I'll improvise this, don't worry, just giving a rough idea. Spine and leaf topology. So maybe they are connected to spine switches like this, right? These switches, leaf switches, right? So therefore it's known as spine and leaf topology. This is not primarily used in data centers. Spine, these are the spines, and these are your leaf switches, right? All these things. So primarily you can keep on expanding as on when requirement goes up, right? You can expand horizontally like this, right? You can keep on adding spine switches and then connect leaf switches to them, right? You can keep on adding spine switches and keep on connecting leaf switches to them. So something like this. Yes, guys. I will not strike off the spine and leaf, but we'll talk of that later on. So for now, two tier. This structure comprises of access layer and core layer, right? Or also known as collapsed core. Done. This is ideal for small to medium sized networks. So if you look at the benefits, the design is simpler and there are few devices, so less investment, right? So that means lower cost and reduced complexity, right? For two tier. What are the limitations? So the scalability will become limited compared to obviously a three tier architecture, right? Correct? And theoretically speaking, or whatever, may face performance bottlenecks as the network grows. So two tier is good as long as your network is medium size, but if it becomes large size, then it's not good, right? Then there you may face some performance bottlenecks. But as your network grows, you can move on from two tier to three tier architecture also, right? Obviously, you'll have to buy more devices and invest more, but because you want scalability, flexibility, right? All those things. So now three tier is what? Obviously, it's the structure is divided into three layers, right? We have seen that core layer and distribution layer and access layer, correct? So core layer, the highest one, which is connected to the ISP, right? What's its function? It's basically acts as a high-speed backbone for interconnecting distribution layers, right? That's the core layer. Access layer, distribution layer, core layer. And these are connected to ISPs. And these are connected like this. So look, none of the access layers are connected to each other. None of the distribution layers are connected to each other. None of the core layers are connected to each other. right? So this is your core layer, this is your distribution layer, and these are your access layers, right? Obviously, I have drawn here layer 3, layer 3, and layer 2, right? So end users are only at access layer. They are not at distribution and core layer. Here only routing will work. Here you will configure routing between all of amongst them. So core layer, this is for high speed, right? Backbone connections, right? Interconnections for distribution layer. And distribution layer switches, these ones, uh, you can configure routing here, policy enforcements here, right? That means you can lay down cost policies or quality of service. I'll tell you this, right? Or security policies. That means access control list. We'll talk of all these things later on. And aggregation of traffic is happening here at the distribution layer. Access layer, it connects end devices like PCs, printers, IoT devices, right? This type of three-layer architecture is suitable for, we know, large enterprise networks. Okay. So benefits are highly scalable. We are talking about three-tier hierarchy, right? So highly scalable and fault tolerant. Modular design here simplifies management and troubleshooting also. The limitations is only higher initial cost and complexity. Correct? Okay. So what more? Cisco wants us to talk about wide area network. We know what a WAN is. Wide area network. Whenever we have the role of ISP, that's through a WAN, right? If ISP is not there, that's not a WAN. That means whenever the communication is between devices which are hundreds or thousands of kilometers apart, maybe from one country or one continent to another continent, we normally say it is a connection through a WAN, isn't it? Right? So this basically the structure connects multiple geographically dispersed location, right? India, right? Australia, New Zealand, Singapore, whatever. Right? Symbolically, we keep on drawing it like this. LAN, connection LAN, one more head office, right? Whatever, routers connected. So this is your WAN, isn't it? And you have multiple ISPs routers here, right? So the primary usage is because business, right? Business means headquarters needs connectivity with branches, right? It could be cloud connectivity or internet connections, right? Whatever. So, and you can use what all technology here? You can use MPLS, right? For connections between head office and branch office. You have to go and tell the ISP. Multi-protocol labels, which in we want to use this technology, or I want to use SD-WAN, right? We don't have everything in our course. Software-defined WANs, right? Or we can use get connectivity through VPNs, or like I said in the olden days, to leased lines, right? We used to get connections. But today, primarily, it will be MPLS VPNs or SD-WAN, right? Virtual private network. We'll talk of VPNs later on. What are the benefits? It enables global connectivity and collaboration, isn't it? Head office requires communication with every branch. So, global connectivity. Flexibility also in connecting on-premise to cloud services, because nowadays things are on the cloud also, right? What is the limitation? High latency and bandwidth cost, right? WAN can be slow, LAN can be fast, right? High latency is delay, right? And bandwidth cost can be high. Of course, security can also be a concern, right? Over public networks. So make sure all your traffic is encrypted and sent over the WAN, correct? So got some idea about WAN also. Where's WAN? So I can strike off WAN also. Yes, guys. What is this small office, home office, SOHO? Look, I'm sitting in my bedroom on a table. I just got a laptop and that too wireless. So obviously we all have some kind of a WAN connection. So maybe fiber to home, right? That is what I have. In the olden days, we had DSL connections. So some cable coming up to my home from the ISP, and they have given a box. You can call it modem, you can call it router, whatever, right? And it's basically a router come a switch because it has got four Ethernet ports. It is a router. It's a switch also. It's an access point because it supports wireless also. It's acting as a DHCP client and server. We'll talk of this because this is coming from the ISP in my home, right? So this guy will ISP will give it an IP address. So it's acting as a DHCP client. So this is ISP. This is my home, and I have taken a maybe fiber to home connection, right? Earlier we had DSL connections. So the cable is coming till this box, and this box has got four Ethernet ports. So I can connect my laptops or desktops, whatever. Or it's I got antennas, so it's acting as a wireless access point. It's a router, come switch, come access point. Plus the ISP will assign it an IP address. It will take a public IP address from the ISP, right? So it's acting as a DHCP client, yeah. And it can also assign IP addresses here, right? To my maybe wireless devices or wired devices. So it's acting as a DHCP server as well as client, right? It's also providing me security. So it's acting as a mini firewall device also, right? It is doing natting patting also. And I'll tell you what this NatPat is later on. Basically, it translates private IP address into public and vice versa. So it the cost is just 3,000 bucks or whatever, right? Because it should be affordable by everybody. So I have a WAN connection. Look, so I'm talking, being able to conduct this small class with you guys, right? So where are we? So WAN connections and small office, home office, isn't it? So it's a home as well as office. So structure is very simple. Typically single router setups with switches and Wi-Fi. So router and switches, they're all just one device, right? We have some switch ports in that router only. So it's router come switch. And also it's supporting Wi-Fi. So the usage is only home-based businesses or small offices, correct? So what are the benefits of this? So it's easy to set up and maintain. And most importantly, it's very cost effective, right? I don't have to invest huge amounts, lakhs and lakhs of rupees, right? Very cost effective. For my small scale usage, right? The only limitation is scalability and performance, right? Theoretically. And of course, security will be basic features that it will support. That's it, not very advanced, or right? Advanced or enhanced security feature it won't support. Yes, guys, all done. Are we clear with WAN, small office, home office? Now, on-premise and cloud architecture. Let's discuss this theory also. Enough of theory now. Last thing, and then we'll jump into IP addressing. Okay. Now we understand cloud and on-premises. Yeah. When you have data center servers in your building only, right, in the campus only, we call it on-premise architecture, right? Whereas nowadays, uh, everything is going cloud-based also because cost-effective, elastic, right? As more demand comes up, we can demand more resources. Virtualization is there. We can spin up servers and machines within seconds or minutes. And practically, we can have anything virtualized, right? Right from servers, switches, routers, firewalls, you name it, right? So on-premise is when we have all the resources kept in our building or campus, right? On-premise service. So on-premise architecture, wherein we have the data center at all the servers in our building only, right? So this is secure, control, full control, we have it, right? Unlike the cloud. So, the structure, if you talk of on-premise architecture, all IT infrastructure and services are hosted and maintained locally, right? That is on-premise. So you're responsible for the security, right? Of course, you'll have to invest in the infrastructure initially. Usage can be organizations which require full control, right? Control over their data and resources, right? So we are not handing it over to anybody, third party. What are the benefits? So benefits can be high level of control, right? And customization. Everything is in our hand. Better data security, right? Of course, depending on the implementation. What can be the limitation of this on-premise architecture? Well, cost, right? Higher upfront cost for hardware and setup. And of course, requires dedicated IT staff, right? For maintenance, upgrades, security, patch-ups, everything, right? If you look at on-premise, now we know what on-premise is. As compared to on-premise, how can we compare cloud architecture? So now we know we have, thanks to virtualization, right? And cloud. So we have some cloud providers. So Office 365, right? I just need an internet connection and laptop. I open a Word file. I think I have saved it in cloud C drive, but actually the file downloads from the cloud, right? And then I think I have saved it in the C drive or D drive, whatever. But actually it's being saved. I work on the file and I close it and I save it. I thought I saved it in my C drive or D drive, whatever, but actually it's being saved in the cloud, correct? That's your cloud. So all your IT resources, servers, storage, applications, everything, they are hosted off-site by a cloud provider, correct? So what is the usage primarily to get scalability and flexibility for businesses of all sizes, right? Medium, small, huge, isn't it? And what's the advantage? Biggest advantage is we don't have to do upfront investment, right? We pay as per usage, right? Pay as you go model. This reduces upfront cost, right? Upfront cost. So I don't have to invest heavily in the devices right now only. And then because internet connection is there, so global accessibility and scalability, right? And now, but the maintenance and updates are managed by the cloud provider, not us. Right? It's their headache to provide security, patches, licensing, right? Everything they have to manage, cloud providers. What is the limitation? The only limitation is dependency on internet connection. So we should have a good internet connection. That's it, isn't it? Which is actually widely and easily available. And India is one of the cheapest, right, internet provider. Okay. But the limitation can also be security because you'll have to now follow some laws legally. You'll be mandated by to provide some good security. So security and compliance concerns with sensitive data. This can be one issue, right? So this is cloud, right? The cloud providers are going to just pay them as per your usage, and they are going to provide you whatever you want. Just you need a internet connection. So as compared to your on-premises, this is the other model, right? Cloud architecture. Okay. You can have a hybrid also. Very sensitive data you can keep in your data center in the premises only. But data which is not very, very sensitive, that can be kept on the cloud, right? Or the data center in the cloud, virtual maybe, right? Whatever, physical, virtual. Okay. So are we done with this basic tats? What is it? On-premise and cloud and yes, we have done all these things. Except for I said spine and leaf, I'll show you the slide later on, but you get some idea about it, right? So rack, it's multiple servers and top of the rack and the top of the rack are again connected to more switches. So it's like similar to two-tier, three-tier hierarchy only. Okay. Yes, guys. All done with this? Yes or no? So now I can pick up a fresh topic, IP addressing and subnetting, which is very, very, very important. You should know which IP addresses we can give to devices and which IP addresses we cannot give to IP addresses. Unicast, multicast, broadcast. What's unicast? Meant for only one. What broadcast? Meant for everybody in this network, right? And what's multicast? Meant for more than one, but not for everybody. Okay. Yes, guys. Everybody here with me? Yes or no? Hello, hello, hello. Enough of theory. Let's get to interesting topic now. IP addressing. Hello, anybody here? Can you hear me?
Yes, yes, you can.
सब ठीक है? All okay?
Yes, yes, sir.
Okay. So now, who doesn't know anything about IP addressing, man? Sorry, where am I? You all know IP addressing? Do you know how to create subnets? Okay. I told you the end story of this after 3-4 days will be boss is telling me branch one coming up next week. Three branches are coming up. Branch one, branch two, and branch three. Right? Branch one, we have 50 hosts. That means you have to give, uh, right, arrange for 50 IP addresses there. Right? 50 host IP addresses. Here we have, let's say, 100 host IP addresses. And here we have 25 users. So you have to make provision for 25 IP addresses in branch three and 100 IP addresses in branch two and 50 addresses or to 50 devices, we have to give addresses in branch one. And boss says, use some private IP address like 192.168.1.0. Take this and now do some subnetting and right, make arrangement so that all these devices next week, they should get IP addresses. You are going to provide IP addresses, right? Is this clear? The end goal, this is practical, real life scenario. Yes, we should be able to do this. Yes or no? Yes, guys.
Yes,
Is it
teacher.
clear? Yeah.
Yes,
But to reach here, we'll have to spend a couple of hours. It's like I want to sing like Kishore Kumar or whatever, right? Singer. I want to sing. But if I join a class, they don't tell me on day one, sing like me, let's sing like this, right? They will perhaps tell me what, sa, I don't know what you call it in English, do, re, mi, etc., right? You get my point. See, if I want to speak English, if I join a class, day one, they are not going to tell me, right, to speak like this. Okay. Okay. The world is on fire, right? It's important to to be disciplined and work every day and study new things. No, day one, they are not going to ask me to speak sentences. They are going to perhaps teach me what? Grammar, right? Verb and adjective. And I'm telling them, what man, what are you telling me? I said I want to learn how to speak English. And you are telling me, okay, wait, this is verb and this is adjective and this is noun and this is pronoun. What nonsense, man. I said I want to sing. You're telling me, okay, do this, re, ga, whatever. I mean, do, re, mi, whatever. But end of the day, they say without doing this, you will not be able to speak later on, right? Or without learning all these things, you won't become a good singer. So to reach there, we are going to look at IPv4 addressing, right? So we know this is 32 bits, correct? And this is in binary. Bits is always binary, right? Zeros or ones. We all know how to convert a decimal into binary and a binary into decimal. 32 bits is what? 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 16. 1, 2, 3, 4, 5, 6, 7, 8, 24. 1, 2, 3, 4, 5, 6, 7, 8, 32. Right? So we know what it is. 8 bits is 1 byte. So every bit has a place value, decimal value. 2 raised to power 0 is 1. 2 raised to power 1 is 2. 2 raised to power 2 is 4. Likewise, 2 raised to power 3 is 8. 2 raised to power 4 is 16. 2 raised to power 5 is 32. 2 raised to power 6 is 64. Double, double, double. And finally, 2 raised to power 7 is 128. So this is going to be our Bible. 1, 2, 4, 8, 16, 32, 64, and 120. And we are going to look at from left to right, right? Highest order to lowest order. So now 8 bits is 1 byte. So we know how an IP address looks like 10.1.2.3 or something like this 172.168.31.111. Just an example, or maybe 192.168. Blah 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 dot blah blah blah. Right, I'm just taking some random figures. So if we know how to convert a decimal into binary, everybody, yes or no? So if I take this 10 decimal, how can I convert it in binary? So binary is I don't want 28, so I want a total of 10. So I can't add 28. I can't add 64 because they are bigger than 10. Lesser or equal will do, right? 32 is also big, so no, I don't want to add. 0 means no. And 16 also is bigger, so no. 8, I want to add 8. So 1, right? So what is this? 0, 0, 0, 0, 1. And I got 8. I only need now 2 to reach a sum total of 10. So I don't want 4. I only want 2, nothing else. Okay, good. So now decimal to binary and binary to decimal, no issue, everybody, right? Then I can proceed. Now look, IP addresses. We know they are 32 bits, 4 octets, right? And it's in binary. So we are talking about IPv4 addressing, right? Not IPv6. IPv6 we'll take up later on. So we have some classes here, class A, class B, class C, class D, and class E, of which in our networks we only use class A and B and C. We never use class D addresses, right? And class E. So class A, what's the range? Yes, who can tell me? Class A IP addresses 1 to 126. Yes or no?
Yes, yes, yes.
Okay. Class B is what range? 128 to 191. This must be memorized, right? On your fingertips. Yes or no, everybody? Class C is what? 192 to 223. Class D is what? 224 to 239. Class E is what? 242 to 255. Class D is used for what? What's the purpose? It's reserved for multicasting, right? And class E is reserved for what? Research and development. पता है ना सबको? Everybody knows this. Yes or no? So when one router sends a routing table update to another router, it may broadcast or it may multicast. That depends on the routing protocol. We'll talk of that later on. Right? Multicast. Understanding? So routers will keep on exchanging routing table updates, right? Routing table copies. So they use either broadcast or multicast or unicast. So we never use class D and E. They are reserved for D is reserved for multicasting and E is reserved for research and development. So we can only use IP addresses from class A or B or C and give them to our devices in the network. Okay. What happened to 127? Where's 127? Yeah, who can tell me what happened to 127? We never use addresses beginning with 127 because they are reserved for loopback addresses, right? 127.0.0.1. So maybe we have given this guy an IP address of 10.113, but its loopback address is 127.0.0.1. And this is used for testing, which means what? This device is not communicating with any of the other devices and vice versa. None of the other devices are talking with this host A. So what do? I go on my this host and I ping my own loopback IP address. Okay. So application layer, physical layer, 7 layers. So it will ping without touching the LAN card, it will come up. So if it pings my LAN card, if it pings my this loopback address, that means TCP has been properly installed, no software issue. Got it? But if it does not ping my own loopback IP address, that means there's a software issue. TCP needs to be reinstalled. So when the operating system was installed, TCP was not properly installed, right? It means, of course, it doesn't come in my course, right? But so loopback. So we never give addresses beginning with 127 to any of the devices in our network. Okay. So everybody remembers this range. I hope there's nobody who will say, I don't remember this range, right? You have to remember this full range and full purpose also. Okay. Now, class A and B and C. A, B, C. 1 to 126, 128 to 191, 192 to 223. If you convert any class A IP address in binary, the first bit will always be 0. Yes? How do you convert 1? 1, 2, 4, 8, 16, 32, 64, 128. 1 is what? This is 1, na? So first bit is always 0. Try and convert 126. Okay, what is this in binary? Decimal. Listen, how much is this in decimal? Yes, who can tell me?
128.
Correct? This is 128. How much is this in decimal?
128 plus 64.
Correct. How much is that?
192.
Correct. 192. How much is this in decimal?
224.
Correct. 224. Right. I know it can be boring, but believe me, this is going to be very important. And especially who's new to this. And how much is this? Yeah,
240.
correct. 224 plus 16. And how much is this? 1, 2, 3, 4, 5. 5 on, 3 off. So now,
248.
correct. And 1, 2, 3, 4, 5, 6 on is how much?
252.
Wonderful. 252 and 7 on
54.
254. And all 8 bits on is how much? 255. Correct? So we can't go beyond 255. Okay. So if you convert any of these bits, 126, look what it is. So this will be 1, 0. Sorry. It will be 0, 1. 0, 1. Correct? No, sorry. Where am I? Okay. Convert any class B, it will be 1, 0. Correct? Convert any class C, it will be 1, 1, 0. Yes? So these only these bits are reserved. We don't have to do anything. Just remember this, right? Class D will be 1, 1, 0, right? Something like this. Just remember this. Okay. Every IP address has got a network portion and a host portion, right? And the subnet mask tells you how many bits are in the network portion and how many bits are in the host portion. A class A, we have 1 octet in the network portion and all the rest in host portion. Class B, we have 2 octets in the network portion and rest in the host portion. Class C, We have 3 octets in the network portion and 1 octet in the host portion. Now this is a rule, right? Is this okay, everybody? Now tell me, class B is used for medium size of a network. Then for class A and class C, which one is used for big size of a network and which one is used for a small size of a network, and why? Yes, who knows this? Who would like to answer? Class A is used for small size of network or big?
Big.
Big. Why big?
Not because
Because,
has many hosts.
correct. Because you have 24 bits in the host portion, right? 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Correct. So 2 raised to power 24 and minus 2. These many usable host addresses to these many devices you can give addresses, which will be more than 16 lakhs, right? More than 16 lakhs. For class B, you will have 16 bits in the host portion, 8 and 8. 2 raised to power 16 minus 2. That is 65,536 minus 2. 65,534. These many addresses. And here, 2 raised to power 8 minus 2 is only how much? So, for small size of network, we can use class C because the number of bits in the host portion is less here, because the number of bits are more in class B, 16 bits. So therefore 65,534. And class A, 2 raised to power 24 minus 2, which is going to be too many, right? More than 16 lakh. So to those many devices in a LAN or a network, you can give addresses. Okay. So remember this, only 1 octet in class A in the network portion. It's a rule, fixed, right? And rest by default can be in the host. Class B, 2 octets in the network portion, 2 octets in the host portion. Class C, 3 octets in the network portion and 1 octet in the host portion. Okay. Any doubts till this point, guys? All okay? So, okay. Now, supposing we have been provided with a class C IP address, let's say 192.168 dot blah blah, right? Dot blah blah. I'll take something. So now, by looking at this only, you decide whether it's a class A or a B or a C, right? Class A is what? 1 to 126. Class B is what? 128 to 191. Class C is what? 192 to 223. So if I tell you 50 dot something 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 is which class? So you'll tell me this is belongs to which class? A, right? Because you only look at this. You don't look at this. And you also don't look at the subnet mask, right? So it's known as FOR, first octet rule. First octet rule, right? If I tell you this address belongs to which class, you will tell me class A, isn't it? By looking at this only. You don't have to look at the subnet mask also, right? You don't have to look at this. You don't have to look at this. If I tell you 150 dot blah 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 belongs to which class, you will tell me it belongs to class B. Why? Only by looking at the first octet, you don't have to look at the subnet mask also. You will tell me this is class B. Okay. Understood this? Class B, class A, class C. Now, the issue is we'll start like this 192, 168, blah, 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 blah. Some IP address. Okay. Before we get there, class A, network portion, host portion, host portion, host. Network portion is always on, which means in the subnet mask, you will have 8 bits on. 1, 2, 3, 4, 5, 6, which means it will be 255. And host is by default always off. 8 bits. So 255.0 dot 0 dot 0. Correct? Class B, this is a default subnet mask, which means only one network, no subnets. Only one cake, no pieces. Only one hall, no walls in between, so no rooms. So this is a default subnet mask, default subnet mask, which begins with 255. What about class B? Network, network, host, host. So 255.255.0.0. This is the default subnet mask for class B. And class C, we have network, 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 and host. So the default subnet mask will be, it's a rule. Network portion is always on and host is always off. So if you see any class A IP address with this subnet mask, that means it's a default subnet mask, which means only one network, no subnets. Likewise, if you see any class B IP address with this subnet mask, which means it's a default subnet mask, only one network, no subnets. Likewise, if you see any class C IP address with this subnet mask, again, that means that's a default subnet mask. One network, no subnets. Which also means if you see any class C IP address like this with a non-default subnet mask. Now, if you, this is the default. So which means one network, no subnet. But if I change the subnet mask, if I tell you it is any number, but not 0. So which means what? This is not a default subnet mask. Which means what? This is subnetted. Which means what? It is not one network, but maybe there are multiple subnets. That means it's not one cake, but maybe you have cut it into multiple pieces, smaller. So subnets. Or it's not one big hall. You have constructed two walls. So this is room number 1, room number 2, room number 3. I mean, I am telling here just as per the diagram. There could have been multiple walls and multiple subnets. Got it? So then there could have been more subnets. Got it? So, but the issue is, are you understanding this? Are you understanding default subnet mask and a non-default subnet mask? Default subnet mask means one network, but a non-default subnet mask means it is not one network, it has been subnetted. That means smaller pieces of the bigger network. इतना समझ में आया? Understood this much, guys? Yes or no? I don't see a lot of time today. We can wind up today here. Aditya, Dipti, Megha, Neeraj. Is it clear or not?
Yes, DJ.
Good.
Yes,
Wonderful.
sir.
Yes,
Yes,
sir, understood.
Wow. I'm so happy. Wonderful. Everybody's understanding that means, right? Good. So that means tomorrow we can go ahead with hyperthreading and subnetting. So tomorrow I'll tell you how to break a network into smaller subnets, right? And which addresses we can use and which we cannot use, and why did we put in that formula -2, right? 2 raised to power n -2, right? All these things, details will keep on coming, don't worry. So now we have come out of a lot of theory, and now we are going to get into, of course, a mix of theory, practical. But now we'll have more practicals also, right? Not continuous theory, but little bit of theory and followed by practical. Little bit of theory followed by practical, because the topics will keep on changing, right? So if everything is okay, we can say thank you so much. Good night. See you tomorrow.